Thank you so much for joining. We have a triple treat this morning. I invited one keynote speakers and they multiplied to become three keynote speakers. So I want to introduce Alan, who will introduce then later Bob. I'll go in alphabetical sequence here. Bob Goodman, and then Carolyn Stout, who is joining from over there, not very far from me, because we're more or less neighbors. Alan has been a tremendous source of inspiration for me. First of all, with the book he wrote, which I mentioned on Wednesday, which inspired the course I described on Wednesday, Who Owns the Learning. And I was happy to see in the abstract, Alan, that you'll touch on the whole subject, the ownership of learning. And then from a conference that Alan has organized many years. When did it start, Alan? Like 20 years ago? No, you're muted, Alan. You're muted. You're muted. Click the
20 years.
20 years ago, and I had the pleasure of being there a few times, building learning communities. And it's been a phenomenal. Each time that I went there, I've had a phenomenally good time with the 1,000 attendees, mostly from K-12, but some also from higher ed. Alan, they're here to listen
Eric.
to you, not to me. So I'm turning it over to you.
I got delegated from you, and I took the lesson, and I'm delegating. So with me today, more important than me, is Carolyn Stout and Bob Goodman. And I met Carolyn, gosh, more than 20 years ago. When she was a teacher, she had built 7 interlocking geodesic domes in a cornfield in Ohio. And she had won a grant application of innovation. And I was so blown away by her application. I was running this nonprofit foundation, and I flew out to Ohio and saw a whole community could live and work in these domes. And Carolyn will tell you more about that. But she did that when she was a teacher, including shipping a submarine from London to Ohio. You'll have to hear that story one day. So Carolyn has no walls around her. And these days, she's the chief scientist with lots of experience designing probes in physics and other subjects. And I know you're going to be impressed with her content when she shows you what's available for you every day. And Bob Goodman, I met, I forget how many years ago, and I was hanging out in one of the roughest neighborhoods I've ever been to in Newark, New Jersey. And I wanted to see one of the toughest schools that were overcoming every aspect of poverty you can imagine. And everybody said, you have to go see a classroom Bob Goodman set up. Now, he wasn't there, but I was watching teachers he had trained, which is even better. And every kid in that class in Newark was totally focused and felt a sense of responsibility and respect for their teammates. It was all team-based learning. It was one of the most amazing things I've ever seen, because I've been all over Newark and I've never seen anything like that. So I've seen Bob's results of both his content and his process. So it's a credible honor to have Bob join, and you'll hear more about Bob and Carolyn later. So I'm Alan November. I don't know anything about physics, but I happen to know Eric, and I've been very influenced by Eric in terms of peer-to-peer instruction. That part of what he does fascinates me. So I want to get right to some peer-to-peer instruction, and hopefully it will either resonate or not, but I hope it provokes thinking is my best hope here. So I'm going to share my screen, and I'm going to go to the desktop and head off to show you a video of a student at the time was in high school. This actually is from my conference. Her name is Shilpa Yalagada. And Shilpa, well, she can explain her own. Here we go.
Textbook. And textbooks are really interesting. Like, they're very helpful in that they have all the material that, you know, your teacher should be covering in class. But unfortunately, they're not very exciting, especially like after midnight, you know. you're trying to like look at the pages, and it's a good pillow instead of like a textbook that you're supposed to be really learning from. So something else I could try is like, asking a question on an online forum. But, we don't really know the credibility of the people who answer these questions. I mean, who is Woo? So, one of the things I ended up doing is actually finding video tutorials online on YouTube. And that was like amazing for me because, you can really hear someone else speaking to you, you hear their voice, they relate it to like, real life examples in their life. I found that very helpful, but sometimes the problem with the videos, like for this one, for instance, I guess it's a little blurry because it got zoomed, but this video, it says it's 13 minutes, and that's really long, especially when it's like late at night, or if you're a student and you don't really, just humans in general, we don't really have a long attention span. So 13-minute videos are like millenniums for us. And can you really like find the information you need in that 13-minute video? Like I have a very specific question, and this video is so general. So a lot of times I found myself just wishing that I could just turn to a friend who was in the same exact class as me, same teachers, same material, and they understood it, and they'd be able to explain it to me in a way that I could understand it too, because they were a student and they just recently went through that process. It's fresh in their mind. And sometimes, teachers, they know the material so well that they sometimes forget how to explain it to students who are learning it for the very first time.
Okay, I want to just stop it here. Teachers know the material so well, they forget how to explain it to a first-time learner. I'm changing her words a little bit. I am fascinated by the curse of knowledge. Some work at Harvard. If teachers know so much, and they can wake up in the middle of the night and explain things, but they may forget what it's like for a first-time learner. So I want to continue, but I just wanted to highlight that.
So I always wished, video tutorials was so great. Why couldn't my friends just make them? So I looked online. I couldn't really find any like student-made video tutorials. So after some time, I was like, oh, like it seems really fun to like make videos. Most 17-year-olds would think that's fun, right? Staying up late and just recording videos. So I convinced my dad to get me a tablet for like my birthday present, and then I started spending really late nights.
Here, I'm going to jump to what she did. She organized her friends to make videos on a school server that would be available to lots of other kids.
I saw like the outfits that we were like picking.
I want to give you a physics example of
one
of these
Joyce
videos.
thought this was so cool, and she wanted to make videos too. And little did we know, she actually ran a tutoring club at school. So this was something that was quite down her line. So
let me get going here and
see.
Hey guys, it's Roya, and today I'll be talking about position. Position is defined as an object's location in relation to a reference point, and that's usually labeled 0 if you're working in one dimension.
I guess it's not showing up completely, so I'm
She's just going to restart it in
possible
her
to
talk.
put it here instead.
Hey guys, it's Roya, and today I'll be talking about position. Position is defined as an object's location in relation to a reference point, and that's usually labeled 0 if you're working in one dimension, or the origin if you're working in 2 dimensions. Now, say there was this really cute guy sitting in the movie theater, and I wanted to sit next to him because maybe we'd strike up a conversation or something. I don't want to be too obvious, I don't want to sit one chair away, but maybe I'll sit 2 chairs away. And if I want to do that, I have 2 options. I can sit here, or I can sit here. These are both the same distance away from the boy, but they're at different locations in space.
Okay, I'm going to stop it there. The story that goes with the content, the cute guy in the movie theater, is the important part of showing this video. It turns out that the stories could be really, really important to a first-time learner. And in this case, probably most teachers aren't going to talk about cute guys in a movie theater when they're doing Delta X, but kids can. And I'm fascinated by Shilpa's work in realizing that how the content is delivered associated with stories can have a major impact in student focus and learning and asking more questions because they can relate to the story. In fact, she got a request from Colombia to translate this content into Spanish. And they had enough Spanish-speaking kids. She's in California, and they started translating. And they sent some videos down, and the project coordinator from Colombia said, stop. Those stories don't work here. It's not going to work out. It's the story, not the physics, that makes the difference. So one thing I want to highlight is, especially in COVID, I think we have a major opportunity for physics students and any subject to make incredible short little videos where they tell a story that a first-time learner can understand that teachers might not deliver themselves. So that's idea number one, that we have underestimated students producing videos. But I would love to see a national library of student videos telling stories that really make sense and captivate kids. In fact, one day I was teaching some kids about screencasting, the tool that made this. None of them were taking physics, but I was showing a physics example just to give you don't need to be an artist, you can do stick figures. And I stopped it right about here. And all the kids said, keep playing it. We want to hear it to the end, because they were so enthralled by the cute guy in the movie theater. We went on to Delta Y. We did the whole video, and kids understood it. They weren't taking physics, but they wanted to learn physics because it was in the voice of a fellow student. So that's idea number one. And then I'm going to do one more before we go on to Carolyn, especially in COVID. Yeah, I'll do this one. This happens to be AP Calculus notes. I don't have an example in physics, but it would be similar. This is a friend of mine who teaches in Manitoba. And what he did was he picked one student every day to be the official scribe. That's a lot of pressure, by the way, because all the other kids know that there's one student who's responsible for making sure there are perfect notes that are distributed to everyone within hours of the class. And you can see these are just different examples of different kids taking notes. Some do color. By the way, I'll just tell you, this kid was a goth kid, didn't have any friends in class, did amazing notes, now he has friends. It works good for social emotional intelligence that all kids are contributing. But what was really fascinating as a staff development, for those of you who want to grow every day, you want to get better and better and better every day, read one student's notes and meet with that student. Here's what happened to my friend Darren, who did this. He would meet with them to make sure that the notes were perfect before he published them. And he realized the notes were often incomplete, missing some key aspect. And the student would say, you never said it, or you said it this way. And it was an amazing reflection for him to every single day meet with a student to understand how they made meaning of his class. He is one of the most powerful professional development experiences I think anybody could have. All right, so there's two ideas for student voice, making videos, and a collaborative note-taking opportunity, documenting learning, and all kids get helped, but also the teacher's reflection every day of how well they're teaching. So from here, I'm gonna jump to reintroduce Carolyn. Carolyn's current work is making probes. I'm fascinated by what you can do with real time, really understanding data analysis, which I appreciate is an abstract idea. Carolyn's work can make it very concrete. She also has the heart of a teacher, so she understands first-time learners. So Carolyn, I'm just going to turn it over to you, and I know the audience is absolutely going to love your content and your approach.
I love how you sell people. That's great. Thank you.
I'm sold.
When I was in the classroom, I taught chemistry, physics, and math for 20 years in Ohio. And it was the last 5 years of that. I met Alan November. And yes, I was working with geodesic domes. And those geodesic domes, he didn't tell you, were opened up for a week at a time every 2 years. and 125 students lived inside without adults. So they actually had specialty areas that they did. So some were robotic specialists, some were medical specialists, and the training that they had prior to going into the domes lasted probably the first semester with the basics that they would teach. We would teach them, and these are 8th to 12th graders mixed, for an entire year. And then the last semester before they went into the domes, we brought in corporate specialty people to help them and assist them. But that wasn't what I was going to talk about. I was going to talk about a program. Even though I taught high school, I also taught during the summer a program at Case Western Reserve University called Retraining Physics Teachers. Because in 1990, when we first went to the Howard Hughes Foundation, in the past 5 years, there'd only been 2 physics teachers in the state of Ohio that had been certified. And so we were trying to think about how could we take that next step to take already existing math or biology, chemistry teachers and really work with them to do physics. And I have to say that over the 10 years that I did that project before I moved here, in fact, the last year I worked it, I went back for the summer. I enjoyed so much working with teachers and building equipment in a lab for half a day. I ran a wood and metal shop, and we built equipment, and then they would go into the classroom the other half of the day with us, and they would actually go through all the physics, especially in mechanics and mostly mechanics. We did a lot of mechanics, but we covered everything they needed for certification by the end of a complete year. So we would bring them back on weekends too throughout the school year. So I was really excited when Alan said, would you like to share some things? And I guess over the years, having taught high school, college, and now for the past, believe it or not, 23 years, I've been at the Concord Consortium since it started with Bob Tinker, and I was brought in to work with sensors. And I'm really a strong advocate of taking real-time data. But at the same time, I have had large National Science Foundation grants trying to understand what the students know about the data. So we had a 4-year project called Smart Graphs. I had another one that I was PI on for graph literacy. And basically, it's really, really hard to unpack student learning because we always assume something that they know. And so I'm going to take you through something today that hopefully will show you how you can build and unpack the student learning. So I just want you to know that at the Concord Consortium, I built this not in PowerPoint, and I built this so that I could show both the probes and the models live. But we have something in the Concord website, which is just simply concord.org, and we are an open source house. And I checked out some of your spreadsheet. You have PhET, you have Pivot, but you also have some of the Concord models up there in that very expansive spreadsheet of models that you collected during this week. But this happens to be on our site. It is keyed into the next generation science standards. So if you pick a DCI discipline, and then all of these practices are what we are known so well for. I'm just going to pick using models right now and go to energy. You will see, I'm only showing 3 because I'm inside the Learn portal, but there are hundreds of activities that you can share with your students at any time. You just click on it, and you can also, as you will see as I go through the presentation, any model that I have, I can click the share button and I can put that into a Schoology. I did want to just respond quickly about what has happened because of COVID for us. Presently, I have 3 large grants, multiple states. One of them, unfortunately, was called Waters, which is looking at watershed advocacy. And it was in 3 different states. And California had completed their implementation before Pennsylvania started. And each state was trained, and our 3rd state is Virginia, separately, usually face-to-face. So we had the face-to-face training, and the students had completed the activities in California. And unfortunately, COVID hit. So Pennsylvania went all online. And I do want to caution you about a couple of things if you're working with students in across the country. They were not allowed to use Zoom. It was a political statement by the school district in Pennsylvania, so everything had to be asynchronous. We did use Schoology, and we did have appointments that they would do by email or phone with their students. But I want you to know that studying a watershed and walking your schoolyard is pretty hard when you're not at school. So everything had to be made into these small videos. And we're about to do that again for all 3 states, starting with a training in August that will be handled on Zoom for the teachers, but we are trying to make everything. And the other thing is some of the schools do not allow YouTube. So you have to really be aware that certain things that you cannot do. So I just decided, based on Waters, to come up with an activity that will hopefully show you my feelings about student understanding and how you have to really think a little bit about what they bring to the table. So here's a situation. I've done a lot of work recently on another project in Alaska where you have a mountain stream that flows into a warm lake. And I am going to see if I can see chat now. So I have to kind of go to more and open my chat one more time. And I would love to have some people tell me, what effect does the cold mountain stream water have on the large warm lake? What do you think? It's based on your responses that will help me understand what you think your students would bring to the table. Changing temperature of water, okay. My answer to that is, or my question to that is not an answer. Drives convection, adds nutrients, great. Equilibration causes convection. It's the second time that word was used, convection. It's interesting, and whether students would understand what that is. Adds dissolved gases. Water temperatures mix where they meet. Kills life if it's too hot. Awesome answers here. Changes the biology of the lake. So I'm not going to type any of those in just because we have limited time. And I'm just going to start with a question here. If I were to fill a cup with cold water, no ice cubes, and let me do that right now. I'm going to do just 100 milliliters. I have some cold water here. And let's see if you can see what I'm doing as I pour it in. I'm going to put it in. So I'm going to run this live. I'm going to put 100 milliliters in and hopefully not sink my computer into water here. I do have a tray, but I'm not over the tray. So this is my cold water. I put it into a cup and I just put it in a styrofoam to try to keep it while I'm talking. And then I'm going to put some hot water in here, 100 milliliters, equal amounts. While I'm doing this, can you come up with a formula or an algorithm? Because one of those practices is computational thinking. For what would happen if I knew the temperatures of the cold and the warm water, what would happen when I mixed them? Any suggestions? How could I figure out what the temperature would be before I mix it? Is there a way you could predict that? Weighted average mass and temp absolute. Amounts of water are the same. The temperature of the mixture might be the average of the two. Ooh, T1 plus T2 divided by 2. That looks like average. Volume divided by temperature. Interesting. So let me figure out what the temperature of each one of these are. Now this is going to be a little hard with my Zoom covering over. I'm going to open my sensor tag. And let's see, this is the cold water, so I'm going to put it in there. And I'm getting a temperature of 13.8. So that's the cold water, 13.8. And if I had a chart, I could put that in, but I just wanted to do a real basic one. Now I'm going to do the warm water. It's 31.74. Probably should have reset and started. Okay, it's up to 38. Let's just say 38.79. So let's make it 38.8. And what were those formulas? One said average. Now I'm going to pour them together. So there's the warm water and the cold water. And now I'm going to take a reading and put that in here. I have to reset. Actually, I'm going to do something a little bit different here. I'm going to stop this, exit, and come back in. Just reset it. So the combined temperature is 27.13. Is that the average? I'm doing it quickly in my head. Was 42.6 divided by 2. Close. Pretty close, right? Easy. Every one of your students would be able to do that. Let's find out what they understand about that average. So here's a typical question. What happens inside the glass when the warm water is added to the cold water? What would happen if you pour these two together? Why do you end up with an average? That's my question. If you were asked your students, these are some of the results you might see. This is scary. Layered, there's no mixing there. Oh, let's not put, them at the top of the glass, let's put them at the bottom, but still layered. But here's one that's got some mixing. And I heard words like convection, which is awesome. Also wonder if they think in terms of what would happen if you were to mix these two together. So here's a molecular workbench model. And the problem I have with this simple demonstration is oftentimes we think of temperature as being an extensive property. It grows. Like, for example, if I were to heat the left here, it doesn't look like I added any molecules. Or if I cool the right, temperature is not extensive, it's intensive. It deals with speed. So what you see here, if I heat the left, is more of these become faster in speed. And if I start this, let's see how they actually mix. It's going to count down and then it's going to remove the divider. My Zoom box is right over there. Oh, I should probably. Do you see the change in temperature of those that are fast? They're colliding with those that are slow. And what's happening? Why is the temperature on the left going down and the temperature on the right going up? Why does it almost look like it's equilibrated? It's dynamic, it's still moving, it's still popping. Anybody want to take a stab at that? Energy is additive. Interesting. First and second law of thermodynamics, okay. What about Maxwell's demon? I love reading these chats. These are great. Well, my contention is that it's real basic and they don't quite understand. So here's another model. I love this model, just 2 particles. So when we added heat, we didn't increase the number of particles. We actually were increasing the speed of the existing particles. These are 2 particles and it's really basic. I'm starting with a really simple here. And they will attract one another. And as they get closer, there's something going on there. Maybe a better one to show you. Let's try this one instead. This is a real simple, call it Newton's cradle. Getting back to that first and second law there. Newton's cradle. I have a little one here that you can show or demonstrate. And what's going to happen is, let me turn off some of this stuff. Let me turn off the shading first and the force. And this one on the left is going to move through. Turn on that kinetic or energy of motion. And you can see, and by the way, this is totally elastic. So the walls are also allowing it to bounce back. And you can add the force vectors. And what I really like about this demo, is this doesn't look anything like those 2 containers that we had where we removed the center. So let me just show you what might cause that to happen. In a liquid, not so much in a solid because it's going to stay in its lattice structure and it's going to wiggle, but and in a gas, those collisions, if they are elastic, are going to transfer that energy. So here's my question to you. I'm going to pause this because I'm on it inside something. What if we did 2 of these? What if we shot 2 at this line? What would happen? Nobody's writing. The 2 on the other end would come off. So what you're saying is if I pulled these 2, well, I don't know if I can do it with my hands not getting in the way there. Can you see that? I think someone had it. Let me do that. Now, of course, nothing is totally elastic on the macro side, but this is on the micro side. So here's my next question to you. Based on what you just saw, can you come up with a formula? We were pretty right on with the average for equal amounts. What if they aren't equal amounts? What would be the algorithm or the formula if I knew the temperature and the volume and I were to mix it together? Can you come up with a formula? I'm going to put different amounts in here. Just watch the top so I don't go over. So I'm going to do a 100 milliliters of one. And let's do 200 of the other. When I test them, I'll tell you which one's the warm and which is the cold. Besides spilling all the hot water on the tabletop, I think I'm okay. I'm just putting them back into these cup containers. There we go. Be close. Talk to me a little bit about the balance beam. We've done that for a couple of things. We have a free-handed one. And by the way, I will give you access to this Learn activity, and I'll show you how you can actually find the models and share them with your students, and also the sensors. And I'll talk a little bit about sensors. Put aside your memory. Anybody have a formula there yet? And I can type this in. M1T1 plus M2T2 divided by, Anybody want to vote on one of these? Think about part over whole. We have 100 and the other one is 200. So the total volume is 300. So part over whole times the first temperature. Plus part over whole times the second temperature. So let me test them, give you some values so you can see. And I may have to do this again. I'm going to exit and then try again, just because I'm running so many in the same thing. Okay, so this is the 200. And even though it's not graphing, it's giving me 38.07. It's because I didn't hit play, I think, or start. Yeah, there we go. All I really need is the temperature on this one. So let's call it 37.8. Need to write that down. 37.8. And that's the 200 milliliter. The 300 I'm going to actually move to this one just so that I can get it to, I should have stayed there. Exit and start again. There we go. And it's coming in about 14.1. And that's the 100. Somebody tell me what they think the temperature is going to be. And I'll mix them together. We may need a bigger container to do that. $29.9. Okay, I'm looking at the formula. Interesting. Okay, so let me move to 15. Put it in. And remember, I'm not perfect. It probably didn't. So really close to 29.4. And really seriously, if I had more time, because a 30-minute slot wasn't a lot, I would have little movies and everything, but I just wanted to kind of do it live for you. But it looks like part over whole times the temperature seems to be part of that formula. So let's see if you can do a transfer here. Based on what you just saw, here's another model. And while I have these models open, all of these models have a share button. So you can actually click on them and copy this share into whatever platform you're using. So the question for you is, this is at 100 degrees. And based on what you just saw with collisions, and this is 50 degrees, this little thermometer over here will show you the temperature. Which one will warm up faster, the top one or the bottom one? And why? The important question is why. And I'm waiting for some answers in chat. Yep, it's very similar with Lillian's. Yep. One of my Bibles when I was teaching. The bottom because they move faster. So this is 50 degrees, this is 100. See if you're right. It was definitely the top. Remember that it isn't increasing the number of particles, it's increasing the speed. So as the temperature goes up, they're moving faster, they're colliding more, they're able to transfer that energy. Does that make sense? So what I was trying to show is now look at it in a different way. It's a transfer activity, but know that inside here are some particles. They have high kinetic energy. Here is the same amount of particles, but with lower kinetic energy. And when I reset this and start it, it's almost like I opened this or connected, and it's conductivity here, connected this piece to it. It could be metal, we'll just call it metal, and see which one will heat up the faster or the fastest. Big difference in rate. Here's another one. Now they're equal temperatures. One's thinner, one's bigger, wider. Which will heat up faster and why? Oh, you're on iPad, I'm so sorry. This could be metal, it doesn't have to be fluid, but you could be fluid too. It could be either. Good questions. Bottom one, more area. More area for what? What's there more area for? More collisions, more bouncing. Okay. That's exactly what happened. So there's one other situation that what I've been showing you are models, and I've been showing you probes. And the two haven't really met other than in concept here. But I'm about to show you something called the thermoscope. And the thermoscope, oh, by the way, I've been using a fast response temperature sensor. And I have a fairly new MacBook Pro, so I've been using a connector that's powered to be able to use the old Go links. And I'll show you where you can get any sensors if you would like, and they vary in cost. This happens to be a wireless sensor that I've made in-house. It has two fast response temperature sensors, and it has a small board and a battery in a nice little food container that I bought off the shelf at the local grocery store. And when I turn this on and connect it, I can do a wireless connection, and all of the sensors that run in the other windows also can go wireless too. And I'll show you where you can get those. And now this lit up. Funny story, I had these in a suitcase in Barrow, Alaska, and they had to search my suitcase, and they opened up and pressed on this and it lit up, and it stopped everything at the TSA because they go through everybody's suitcases. But I'm known for carrying lots of equipment with me. So here's an example of what you can do. And if I were to use the sensor, let me again put some water in here. And I'm not going to be exact this time. I'm just going to put warm and cold water in. So that's cold. And then I'm going to do a warm. And by the way, Eric, if I were using my Zoom, I would be able to show everybody what was going on my table, but I couldn't make it work with your very long numbered Zoom. So I'm going to put a sensor in each one of these. And you can't see that. So I'm going to hold those up. So the sensors are in the cups. And then I'm going to get a nice little reading. 38 degrees, 13 degrees. And you can see they're labeled A. And the 13 degrees is moving a lot slower. Well, actually it's 14 now, than the 38 degrees. So there's a difference in speed here being shown. Now, if I mix these, put them in, whoops, that's probably not what I want to do. I mix those, too many water things. It's going to put them together, and it's going to show the change in temperature. And they're both reading 26 degrees now, but you can see the ghosting of where the temperature was before. By the way, we're using this setup not with high school students, not with middle school students, not with elementary students. We're testing it with kindergartners. So to me, understanding why something is a solid, liquid, or a gas, and not memorizing, but understanding it at a very early age, can help students understand as you get deeper and deeper into it. In one of those models, I could have turned on charges. So let me go back to that so I can show that. I think it's here. Let's see if I can turn on, was it probably somewhere around here? No. Maybe here. I think I did have it right the first time. I think I could turn on charges, maybe not. There, maybe it's later on. Ah, here you go. So even though we're working with very basic models, you have to start with the basics But then you can go even further. You can change what we call the attractive forces, van der Waals. You can change the temperature. Let's get these back pretty much together. And oh, by the way, I can even put charges on. So just so that I'm trying to not confuse you, I just want you to know that it's very important to unpack. Start at the very beginning and figure out where their understanding is and build upon that. So all of these resources you can find at the Concord Consortium. When you click on resources, you can sort for the different types. Everything that was in your spreadsheet was a single model. We have complete sequences of activities that build from the beginning and take you through these levels of understanding, and they're called sequences, and those are available. Here's a good example of one. This is in Inquiry Space. It's a collection, and you have starting with Investigation 1, Investigation 2, Investigation 3. And I built this in the Learn portal, and if I could have followed all 200 teachers or whatever, I could get a report. Actually, we found that 100 is probably the maximum per class right now, but we can build up that capability. But I would be able to see all of your answers individually, and I would be able to share them if you logged in and became a teacher. And all of this is free at the Concord Consortium. So the other one that Alan mentioned was CODAP, and it is also part of Inquiry Space. CODAP is called the Common Online Data Analysis Platform, and that along with Sage Modeler, which is a systems dynamic application that we've been using quite frequently in projects. You can go in and look and explore large data sets, especially in the day of epidemics or pandemics or COVID-19. You could pull down all the information from the CDC, assuming they can keep getting that information, and you could actually make some sense out of it. So I think I'm going to stop there because I'm 1 minute over what I had put on my thing to share. And I hope you save this chat so I can go back and look at it and probably answer some additional questions. And now I'd like to introduce to you Bob. And Bob will be talking about his work at the New Jersey Center for Teaching and Learning. And he's been dedicating to increasing student access to physics for more than 20 years. Go ahead, Bob.
Good morning, everyone. I won't wait for you to say good morning back because you're all muted. But in any case, let me take my time with you today to tell the story of what I've been working on for quite a while and where we've arrived. I think where we've arrived will actually have the most significance because it'll let you know some resources that are going to be, they would have been important anytime, but they become even more important with this world of COVID. Can everyone see my screen? Alan, do they see my screen? Okay. So Physics for All is really the theme of what I've been doing. And the reason I got committed to Physics for All is that when I came into education some time ago, there's always been a lot of talk about STEM careers and STEM majors. And there's a lot of people working to get kids excited about STEM, but I felt like there weren't the proper tools in place or the sequence in place to prepare people to actually be able to enter STEM careers. And there's some simple ways you can see that. One is if you go to the STEM majors at a university and just see what courses they require, you're going to find that 90% of the STEM majors require students to take physics, 80% chemistry. You literally can do this, and I did it by just going to Rutgers catalog or any catalog and just adding it up. So the rank of importance to STEM is physics, chemistry, biology, earth, and space. And by the way, I wouldn't just say this because this is a physics conference. This is what I say to anyone who asks about STEM. Unfortunately, high school students learn in the reverse sequence and in the reverse frequency. They generally learn earth and then biology, then chemistry, physics, and too small a percentage of them ever get to physics. And learning in this sequence has its own fraught with its own problems. So because of that, a lot of kids get to university and they don't have a strong foundation in science because they never got to physics, or if they did, they got to it last when it made the least sense. And they don't have a strong foundation in mathematics because if you don't do physics in high school, you don't have a lot of places to play with mathematics. And you can, this has been very strongly my experience. We've seen huge gains in mathematics achievement based on what we've done with students in physics. And the net result of it is they're unprepared for STEM majors, which is one reason why engineering schools have a 50% dropout rate the first year. Students get to engineering because they hear how cool it is and what a great career it's going to be, but they can't do the work. So in the past, you could shrug this off and say, oh, well, they could just go work on the assembly line in Detroit someplace and make a middle-class living putting wheels on cars or whatever. But those jobs are getting scarcer and scarcer, and it's really just not fair at this point to allow kids to graduate high school without the option of being able to go into a career that requires the mental tools of science and mathematics. So I'm a strong believer that all US students should take 1 year of mathematically rigorous physics and have the option of taking at least one more year. Doing that requires tripling the rate of students taking physics, because right now only about a third of US students take physics. There's also dramatic racial disparities, which underlies a lot of what's going on now because it leads to gaps in income that show up in wealth and everything else. And right now is a very sensitive time with people becoming more aware of that, although clearly they should have been aware of it before this. And gender disparities. Just to show, I've got a lot of slides on this, but I'm going to show you a few of them today just to show these. Everything I'm showing you about bachelor's degrees also reflects through the data on AP exams and students taking physics courses in high school. So this is physics degrees from 2013 to 2017. Black students represented fewer than 3% of the bachelor's degrees, but they're 15% of the population. So one-fifth the participation rate in physics. So if you think physics is important to STEM careers and you think STEM careers are an important pathway to middle class or upper middle class life, Black students are at a disadvantage right here. Hispanic students, the gap is there, not quite as extreme, but it's still extreme. This shows up in this graph. This is underrepresented minorities, which includes Blacks and Hispanics. And they're about just 35% roughly of the population. You can see that combined, they're about 13%, 12, 13% of the bachelor's degrees. So what is that, a factor of 3? Something like that, of disadvantage. Women were making some progress in this for a while, but actually not so much anymore. This is the blue line is bachelor's degrees earned by women in physics, and you can see it peaked in here somewhere. I guess that's what, around 2000 or thereabouts. But then it's been drifting down. So fewer than, well, right now 20% of the bachelor's degrees in physics are going to women, and I don't think you need a calculator though. It should be about 50% in a gender equitable world. That should be about half. So that led me to this conclusion, which is that opening STEM career paths for all students is critical for social justice, but also for providing, that means providing all students a chance at a good career, a good life. Global competitiveness, because if a country is going to compete, it has to realize the potential of all of its citizens. So it's not just good for the individuals, it's also good for the society. And national security, because you can't have people from other countries taking care of our fighter jets. It just doesn't work. And eventually you reach the point where you actually can't maintain your defense structure because you don't have a sufficient mass. And we got called into meetings in Utah about the fact that they can't find the people to keep their jets flying at this point. It's going to be a real big problem. The problem that we faced in addressing this, and this is what we've been working on for about 20 years, is that courses in science and math are really designed for selection, not education. They screen kids out. They give them barriers at the beginning of the courses. Guidance counselors warn people away. And you end up with even highly integrated high schools looking very segregated when you walk down the hallway and you see who's in the science and math classes and who's in the remedial classes. Teacher shortages, not nearly enough teachers. And that teacher shortages is self-perpetuating because you have so few people graduating that you end up with very few people as physics majors, and with the classic route to become a physics teacher having to go through being a physics major. All those things I just showed you about the shortages, the racial disparity, gender disparity show up on the other side of who teaches physics, and you have a sheer numbers problem as well. So give you a little history, I was in the audio business for about 20 years after I graduated MIT with physics, and I retired from that in 1999, was asked to start a pre-engineering program at a vocational technical school, which is where this adventure begins. That was me a while ago. So I began teaching 9th grade in Bergen Tech, a vocational technical school. And I was hired to start a pre-engineering program. That's where I really got familiar with all these problems. When I got there were no tables in my classroom. They're just computer stations, because they somehow thought that in 1999 people didn't need to take notes or anything. They just needed a keyboard and a computer. I was told by the superintendent, who seduced me into taking this job instead of taking a regular physics teacher job elsewhere, that I was getting these great students who had all had Algebra 1 in 8th grade. First day of school, I asked who had Algebra 1, and only 3 of the 16 students in the class had Algebra 1. So I recognized that wasn't going to work, and I was their vocational teacher, not their academic teacher. So I had to use my 2 hours a day of vocational time to remedy this. And then, of course, the classic American sequence of instruction, which makes no sense at all. So I borrowed round tables from the faculty room. I got there a day before the faculty showed up. I stole all their round tables, stuck them in my classroom, went to the cafeteria, grabbed cafeteria chairs, and suddenly I had created a social constructivist learning environment. Though I didn't know I was doing that, I just needed tables and chairs. And I started to model my instruction based on the model of brief direct instruction, less than 5 or 6 minutes of ever talking at the students, and then giving students increasingly complicated problems they could work at on their round tables together to figure out how to do stuff. And students working around round tables turns out to be very good for, it's actually very similar to what I saw in Eric's class when Alan and I visited, but it was easier for me because I had 20 students in a room around 5 round tables. I didn't have to do it in an auditorium. You can even see the round tables in there if you look closely. So I had 2 hours a day. I taught them Algebra 1. I had to teach them algebra-based physics and Project Lead the Way engineering. And I chose algebra-based physics because, as I said before, but I realized this in '99, that STEM career paths all started with physics. If you couldn't do physics, you weren't going to get into a STEM career path. My job was to prepare people for engineering schools. So that was a no-brainer to me. Also, if you know physics, you can understand chemistry. And if you know physics and chemistry, you can understand biology. If you don't understand physics, you don't understand anything. So there's just no point proceeding forward. And it also it gives a playground for learning math. So I could teach them Algebra 1, and then I could teach them physics that required the use of algebra to solve the problems. And kids suddenly got way better at math when they saw there was a reason they were learning math. They simply couldn't figure out how high the rocket went without solving a system of linear equations. Suddenly they got very motivated. Our school became like the best in the state for mathematics achievement before we changed anything in our mathematics program. It was all done through physics. There wasn't a textbook at the time I started to teach mathematically rigorous physics using just Algebra 1. In the US, if you were doing mathematical physics, you did trig or calculus. So I wrote a book. I spent my weekends that first year just writing a book every weekend and giving it out to the students in Word every Monday. And I chose topics that would prepare my students for chemistry, which was their second year course, and prepare them for AP Physics. And I took the presumption that all my kids were going to take AP Physics. And one reason I settled on AP Physics was that this was a new vocational technical school. I wanted my kids to get to engineering school. No engineering school was going to assume that because I said my kids knew physics that they did. I needed a national test that they could take and compete on. By 2003, so 4 years into this, the word had gone out to all the other majors, the kids studying culinary or fashion design or welding or any of the other traditional vo-tech subjects, that physics was the best subject ever. And they all wanted to know why they weren't allowed to take physics in 9th grade. So by 2003, we had eliminated all tracking in the school. So pre-engineering students sat next to the students studying how to fix cars and how to cook. Found around the same round tables. There was no honors or regular or anything else. Everyone took the same courses. By 2005, my school was #1 in the state for taking and passing advanced placement physics, even though we were more racially diverse and had higher poverty than most other schools in the state. But we outperformed all the white suburban schools. By a long margin, by the way. We were #1. #2 school was half of us, and we were 8 times the state average. As a result, I became the 2006 New Jersey State Teacher of the Year, got to go to the White House and meet the president and such, which is an honor I would not look forward to right now, but back then it was sort of okay. I had finished a 2006 doctoral dissertation, which documented how this program worked and its results. I was asked by the Teachers Union to become one of 5 founding board members for the New Jersey Center for Teaching and Learning, and because I was State Teacher of the Year. And I was asked by the New Jersey Department of Education and the Teachers Union to figure out how to bring these gains to more schools in New Jersey. I'm not going to go back to Bergen Tech anymore. I had to retire from there a few years ago because this job became full-time. But it's worth noting that that school has gone on to become a top 100 high school by almost every rating in the United States at this point, even though its minority enrollment continues at 59%. So at 59% minority enrollment, it's rated as number 13 best STEM high school in the United States, which says a lot about what the potential of doing things right in education can, the impact it can have. But the New Jersey Department of Education wanted me to get more kids in New Jersey ready for STEM careers. And so we worked at NJCTL to extend the work I had started in '99. We had to stop, these are the 3 things we had to do. We had to stop teaching high school science backwards. We had to develop free OER science and mathematics course materials that could be shared and edited, and we needed a lot more physics teachers. And as I go forward through this, you're going to see everything we did that started in physics migrated to everything, because I had to create a chemistry course based on the same principles as a physics course and a biology course for kids who had taken physics and chemistry. Eventually, we had all of K-12 mathematics, almost all of science, all the AP courses in science and math apply. We had all the materials to do all of those, as you'll see. This is the, does anyone, I guess I could ask the question in chat, but I'm assuming that most people know about physics first at this point. I always resisted the term physics first because when I started in '99, physics first was based on a conceptual physics course in 9th grade so that all students could take it. I never liked that approach. I like mathematically rigorous. But this is the traditional, kids memorize stuff in biology, then they memorize stuff in chemistry, then they memorize stuff in physics, then they say at the end of the physics course, oh, now maybe I can start figuring out how this stuff made sense, but it's too late. By the way, most of the kids never get to physics because they think science is boring and a lot about memorization by the time they get here. Also, they're sitting in Algebra 1 saying, when am I ever going to use Algebra 1? Because there's no course in the school where they use it, nothing in their life that they use it. This is the new sequence we put in. Physics leads to chemistry, chemistry leads to biology, physics ends in quantum physics, chemistry ends in biochemistry, it all flows. It could be called Science 1, Science 2, Science 3. Every one of the courses is aligned with the math standards being taught that year. So physics uses algebra, chemistry uses ratios and so forth from geometry. It all sort of makes sense. And you get all these benefits. And it turns out if you teach kids things, if you teach things to children in a way that makes sense to them, they like it better and they learn better. Fortunately, the course materials, as a State Teacher of the Year, they gave me a smart board. And I couldn't figure out how to teach with it at first, but one thing my student teachers and I figured out was I could take all the stuff, we could take all the stuff I had done in Word and move it all into smart notebooks. And then we could put it on a website, which was the original website we had, was basically a listserv of all of our files. And we could let teachers anywhere in the world use these files to teach themselves. We captured not just our content, but our pedagogy. And I'll show you how that works in a second. Well, here it is. Here's a smart board with one of our slides. This was actually done in Africa. We also work extensively in the World Bank. We've spent about 6 years, and I don't have it in this presentation because of time limitations, but if you're interested in Africa, we've created more science and math teachers probably in Africa than anyone else at this point too. But World Bank just published a report showing that we have tripled the rate of students being qualified to go to university by going through our program of science and math. But anyway, direct instruction. Teacher is very fast, 5-6 minutes tops, quick instruction. Then the students sitting around in round groups, doing problem solving. I like round tables. These aren't round tables, but it's heterogeneous. If we find all the strong students at one table, we split them up, make sure that there's always a range of students past student accomplishment. I don't want to say strong and weak because they're strong and weak mostly because of background of what they've studied in the past, and we try to remediate that. But anyway, heterogeneous grouping. We link the format of the direct instruction and the formative assessment by using student polling devices. So we always ask formative assessment questions. We had to write thousands of formative assessment questions to make this work. So here's an example of a simple formative assessment question from algebra-based physics dynamics. So we'd ask that, we'd teach 5 minutes about dynamics. We'd ask this question. The student, when the teacher stops the question, they get a bar chart out. It shows them the answers in the class. But when we first did this, we showed them which was the right answer, but we figured that was stupid. Because when we showed them which was the right answer, we had half the class pissed off and the other half of the class feeling like they didn't have to pay any more attention because they already got it. So instead what we did was we just gave them the answers and told them to find someone with a different answer and convince them why they were wrong. And kids loved going around the room arguing with each other. So it became a very loud, dynamic class. They do like 6 of these in a row until everyone's getting them all right. And then we go on to the next topic. And this is key. Keeping the direct answer hidden was fundamental to making this approach work. We did all of K-12. By this point, we've done all of K-12 in AP Science and Mathematics. It's all for free. Anyone can use it anywhere in the world. We eliminate the need for textbooks. Teachers no longer have to write lesson plan. In Newark, Alan talked about Newark. Newark accepts our, teachers just have to indicate what parts of our notebooks they're going for. That is their lesson plan. So, because our lesson plans, we tied unit plans with all of everything a district would ever require for a teacher to give. We don't want to waste teachers' time on stuff like that. We'd rather the teachers work with teaching, interacting with students. Just for your reference, last year we had 600,000 plus file downloads from 250,000 unique users in all 50 states and 186 countries. If you go to the site, you're going to find 5,400 presentation files. It's more than 250,000 slides, 14,000 Word documents, and we now are up to 30,000 videos posted on YouTube. And those were created to create the asynchronous learning environment that I'll talk about soon. The next problem was we didn't have any physics teachers. We'd go to districts who wanted to do what we did, but they didn't have anyone who could teach physics. So we had to create physics teachers for them. This is a really huge problem that I'm surprised physics teachers don't focus in on more, because it could be done. This doesn't even require algebra to see that what we've been doing in the past will never work. If you want to triple the amount of physics being taught in the United States, you need about 36,000 more physics teachers. Higher education produces about 300 physics teachers a year. About that many retire every year. So we basically are not moving the needle on how many people there are to teach physics. So we're always going to have 2/3 of the students in the United States not able to study physics until you solve this problem. And we're not going to get there fast with people who are majoring in physics, because this study I just found a couple days ago points out that only 2% of physics majors are very interested in teaching. So you're not going to get a lot of physics teachers teaching physics. And if you look at it, there's about 8,800 physics majors in the United States right now. So if you got 2% of them to become physics teachers, you'd get 200 a year. We're really getting 300 a year. Order of magnitude is correct, but it's 2 orders of magnitude below what we need if we're going to have all students have access to physics. So having physics majors become physics teachers will lead for a permanent inequality in our society, where 2/3 of the students will not have access to STEM career paths. But there are 4 million teachers roughly in the United States. Again, just order of magnitude figure calculation here. If I get 1% of them to become physics teachers, I got 40,000 new physics teachers. That's a way easier proposition. So in 2009, we approached the state with our math, and they agreed with us, and they approved us teaching physics to teachers the same way we teach physics to students, but also teaching them how to teach physics while we're teaching them the content of physics. And then the content we use to teach the teachers is the materials they then use to teach their students. It combines together curriculum, pedagogy, assessment, and professional development into one seamless package, way more efficient than the normal model. We've created 282 new physics teachers in the last 11 years. We think that makes us #1 in the United States for creating physics teachers, as far as we can tell. Carolyn, your note about 2 physics teachers in Ohio lines up with this. I've done presentations all over the country, and I always ask, if there's always someone from a university, I ask how many physics teachers they've made last year, and it's usually 1 or 2. So we're 25 a year for every year for the last 11 years. So it's an order of magnitude different. We're also creating racially and gender diverse physics teachers. 16% of our physics teachers are Black, because we're drawing from the pool of teachers, not from the pool of physics majors. 10% Hispanic, which used to be higher. So I've got to figure out how to get that back up. That should be more like 20%. And it's 50-50 male-female. So it turns out if you equally expose everyone to physics, women like it just as much as men. We found the same thing in my high school. Girls took AP Physics at the same rate as boys, but if you go around the country, it's only 20%. So AP results mirror the bachelor's degree results. Our programs, 94% of the teachers who start our program, start the field experience for our program, finish within 1 year. You get another percent if you wait another year, so that's pretty good. 92% of them pass the required physics praxis exam and general science praxis exam. And 94% when we do anonymous surveys at the end say they'd recommend our courses and programs to another teacher. This is what our graduates look like. We started out, the blue is physics, the whatever that color is, I don't know what that, red I guess, is chemistry. You can see chemistry was pretty low for a while. And we went down, we started to dip in 2018 because we started to recognize that there were teachers who wanted to take our courses, but they were not physically close enough to do it. So we made the decision in 2017 to go online. We actually made the decision back in 2014 to start going online, but by 2018, we decided we had to be online. It took 300 hours. Our program was way more efficient. We were producing a lot of teachers, but it still took 300 classroom hours. And a lot of people, that was an inconvenience. And to many people, it was an impossibility. If they were taking care of their families at night, coaching, to have a second job, they couldn't do this. So we went online. We did a lot of experiments. We did live Zoom classes with teachers. We set up office hours with teachers. We did all kinds of stuff with teachers. It all failed. Teachers we end up with our professors or instructors sitting around in an empty Zoom room waiting for someone to show up. And if two people showed up, they had completely opposite questions they wanted to discuss and just got pissed off with the fact that we couldn't get to them first because they had to wait for the other person. So we found that we went totally asynchronous, and we used Zoom sessions for individual or small group instruction for people who had the same problems or needed some extra help. I'm going to show you a video which will tell you all the stuff about our online courses for teachers better than I will, and then I'll wrap up after that to show where we are.
Teachers, are you looking to expand your skills, advance your career toward a subject that is in high demand? Learn from instructors with years of both classroom and remote teaching experience. Help students achieve in both classroom and remote learning environments. We're here to help when you sign up for NJCTL Teachers Courses. We are the New Jersey Center for Teaching and Learning, a nonprofit organization run by certified teachers with years of experience both in the classroom and in effective online learning. NJCTL is a leading producer of science and math teachers in the United States, providing courses that help teachers build the content knowledge they need to significantly improve student achievement. In 2017, NJCTL transitioned its courses for teachers to be 100% online and asynchronous, so teachers can now take courses anytime, anywhere, at their own pace. 95% of teachers who have taken an NJCTL course say they would recommend that course to their colleagues. Teachers can choose courses in both middle or high school math and science, as well as AP Physics, Chemistry, and Computer Science. We've developed an approach to online learning that combines the very best in classroom instruction with the rich opportunities that remote learning provides. Because classes are asynchronous, they can be started anytime and taken at your own pace. Each topic is introduced with a brief video explanation, followed by a series of questions to test your understanding. You'll know immediately if you got the problem right or wrong, and will be provided with a video demonstration of how to solve the problem. Every course unit includes virtual labs, auto-scored multiple-choice quizzes, and virtually proctored exams. Instructors grade labs and other open-ended responses and check in regularly to provide ongoing feedback about academic progress. In addition to learning the content, you'll learn how to teach the content to students by reflecting on your teaching practice and interacting with your peers and course instructors via discussion boards. Through our innovative approach, NJCTL has become the #1 producer of physics teachers. Our work in building an effective, knowledgeable teaching force has contributed to New Jersey becoming ranked #1 in student achievement in physics and #2 in chemistry. we are here to provide teachers with a strong foundation for future success and the joy of learning in courses that can be taken anytime, day or night. Check out NJCTL to learn more about how we can be helpful for you.
So that shows you like how the courses work better than I could explain them probably. And so hopefully you find that valuable. What we've done now, well, having done that, this is the map showing our spread, this color coded by numbers from 2010 to 2019. Once we were online, you could see the entire state was able to join in, where before that, we started out, my school was here, so we started out there. We've now spread everywhere. I'll just show you really quickly, but these are our physics courses. You can see we go, all the APs, all 4 AP physics courses are available, as well as algebra-based physics, trig-based physics is coming out this week. Chemistry, mathematics, computer science, both AP computer science courses, and we have teaching methods and field experience. Part of our endorsement program requires the teacher to teach a first-year physics course and be coached by us, and it's all video coaching, so we don't have to drive to the schools. The next thing that happened in March was that schools started closing due to COVID, and we realized that we had the tools in place to directly help students whose schools were closed, and many districts weren't actually, for lots of reasons, both capability and political pressure, didn't offer online instruction. So we started making our classes available to students directly. So what we did was we took out all of the content about how to teach the course, and we just left the content about about the subject area content itself. We first did it as online self-study courses, which we gave for free to students through June 30th, because we just did it as a public service at that point. We hosted them on our site. Students could just come to the course. Teachers could sign. We had several thousand, I don't know if it was 10,000, but many thousands of students started studying from us online for free. We're going to have a nominal charge for that, like $7 a student, I think, for the schools to do it in the fall. And this is just the physics courses, but all these courses were available and are available to students. And then we decided that those self-study courses are good, but they don't directly link to the teacher. The teacher has to use their LMS to see how the students are doing. They can't see how many hours the students logged in, their last login, all the stuff that you would want to know as an instructor were not available. So we've started the process now of setting up for schools classes on our website, where we enroll the teacher and the students under the teacher, so that the school teacher has all the facility and capacity that our instructors have to work with teachers. They now have that to work with students, and these courses are available now. So and then the last thing is that the first thing we did actually was offer them directly to students, because there were no teachers around to do. The next thing is for us to offer them to students, to schools. So we're doing that right now. And this just for your reference, because there are a lot of people looking for answers, because schools are supposed to open in a few weeks. This shows the features of the elements that make up the instruction. This is what's available for free on the website and underlies everything we do. These are the self-study courses, which still have automatic feedback, all the stuff about videos and trying the problem, seeing a video, virtual labs, auto-graded quizzes, progress bar. That's all there for students right now without a teacher. We add the teacher in, the district can add a teacher in, and that's done by the district teacher. And that's, I think, an order of magnitude better of experience for students. If necessary, NJCTL can become the instructor. For instance, especially like a school may have one kid who wants to do AP Physics C. We could teach that for them, because they probably don't have enough teachers to do all of it. And then these are the graduate level courses that we've now recently been licensed by New Jersey as an institution of higher education. So we actually can use our courses in New Jersey. We're going through the accreditation pathway now for middle states to become a university nationally or internationally. And our courses for students have been recognized by NCAA now as meeting their requirements. So anyway, that's what we've been up to. Thank you for giving me the chance to share all this with you, and we look forward to helping anything we can do to help students and teachers be successful with improving math, science, and computer science education. We're game for. Thanks so much.
Well, thank you, all three of you, Alan, and Carolyn and Bob. This was really so inspiring. So the hands have been going up, and Nicole Harvey has had her hand, and the chat has been going wild. I mean, we're saving it so you can see all that was said while you were talking. And you know, I wish you could hear the applause. I mean, people are applauding on the screen and in the participation list. So we have only a few minutes for question because the next speaker is coming online pretty soon. So Nicole Harvey has had her hand up for a long time. So please unmute yourself and go ahead.
I have a quick question for Bob. I was looking at your statistics and working both with Step Up and trying to work with our administration in our district and in our state. I'm curious where you got your numbers from as far as the number of STEM careers that require physics.
So I actually did STEM majors that required physics.
Right.
And I got it by just opening up the catalog. I did about half of it. My wife finished it for me and just went to everything we consider the STEM major, like if computer science or I included doctors in there and nurses.
Okay.
Like that. Basically
Sure.
technical. And then we just looked down the requirements for the major. If it said physics in it, we check it. If it said chemistry, we did check. And you're going to find that a lot of students show up in colleges not able. My Perkins Grant Advisory Board, I asked, were the deans of engineering schools. So I said, what do you want from me? And they said they want kids who had taken AP Physics, AP Chemistry, AP Calculus, because half the kids drop out the first year before they see their first engineering course because they can't do physics, chemistry, or calculus. So that's where we got it. I'd be willing to talk about it more and share it, but
was there a specific university or set of universities that you looked at?
I used Rutgers.
Okay.
But I think it's pretty common. I think you're going to find STEM major requirements are not so different university, but you can check me. But if it's not 90, it'll be 80. It's going to be very high.
Thank you very much.
You're very welcome.
Next in line, I have Joshua Roth.
Hello?
Please unmute yourself. Yes.
Hello. I am using Zoom on a cell phone for the first time. Thank you. Touched and inspired. It's a narrow technical question for Dr. Goodman, but I'm just wondering if the smart board notebooks are can be open, edited, and so forth by any open source software, or if you have to have the proprietary system.
So the sad answer is you need Smart Notebook to do the editing. The good news is that you can use a lot of teachers use our PDFs on their devices, and you can get a free version of Notebook. Smart doesn't say so much about it, but we have on our site a link to a free version of Notebook so teachers can download that, use it, and they could put it on their kids' devices too, but Smart doesn't work on tablets and phones and stuff. So a lot of people end up doing editing in Notebook and then sharing with PDF, which do open on everything. And by the way, a Smart Notebook slide looks great on a screen, but it looks perfect on a phone. It's exactly the right aspect ratio. And we found when we tested it out that showing notebook slides on phones is just as effective as on boards. In Africa, there's a lot more phones than there are computers. And Moodle, which is what we use as our platform, works on phones and laptops.
Great. I see still one. I had two hands up. There's only one left. Rob Krakel.
Hi. So I actually have a question for Carolyn. With the probes that you were using and Ken using, I think you're muted if you're responding. Is that something you can implement through like a third party? So instead of like a Vernier or Pasco, you can use an Arduino or your own made probe interface?
So Rob, yes, we've been working with almost all of them right now. I even brought with me a little sensor tag, which we've made a smartphone app for. So this has 14 different sensors and it's only $29. So this doesn't allow you to put it into water like what I was doing, but this is what we use in the environmental. And our interface is, we try to do as many platforms as possible. So I'm just going to share for just 1 second because I forgot to show the probe site. there is a site called ProbeSite that we've been keeping up for the last 20 years. And these are the ones that we have supported in the past. And we just made some changes, so we probably would have to do some quick testing. But if you have other ones, or you even have homemade ones, you know, I've been known to make them with 3D printers too, and still be able to do the communication, the handshake. So feel free to write me if you have any additional questions.
Absolutely, thank you.
So it's almost 11:35, at which point we are supposed to have a 5-minute break. I just want to be sure that anybody who wanted to ask a question, because I saw at one point more hands up, has been able to ask their question. So click the participant button, and then, okay, Terry, you get the last question.
This one's for Bob. I really like hearing that the way you're trying to recruit more physics teachers is by going to teachers instead of trying to go to physics majors. It makes so much more sense to me. There's I suppose the organization's called PhysTech that puts physics teachers in residence at local colleges, and I'm wondering, how do I say this? Have they had the chance to see your work? Because it seems they're working at cross purposes.
Yeah, they have an honor roll. PhysTech is a good organization, but the order of magnitude is low in terms of what they create. I think their honor roll is if the university creates 5 teachers in a year, and we're at 25 or 27 a year, so I think that's a good solution. It's a good approach. I honestly, we need all the teachers we can get. So if we're doing what we're doing and they're doing what they're doing, everyone should just do their best, and if we all work together, we'll get there. We did have one PhysTech graduate who worked with one of our teachers in Trenton, and the PhysTech teacher ended up using our materials and switching over to our stuff anyway. So the materials are all free and available for everyone to use. And by the way, there are questions that are coming up, and we're not going to get to them all, but I'm easy to find. You can just email me at bob@njctl.org, and I get back to people really quick.
And I suppose I ought to say that I've been using stuff from your organization for a couple of years now, and it's made a great impact in my class. So thanks a lot.
Oh, you're very welcome. That's great to hear. Thank you.
So as we're right at 11:35, I want to end by giving Alan another opportunity to say something in closing. I know I'm putting you on the spot here, Alan, but we started with you, and you gave us this wonderful introduction to how important it is to teach the content in the context of stories. So, and our next speaker actually will touch on that, use as a story the physics of living systems, biology. So I'd love to hear more about your perspective and on that subject.
Well, the other, I really have can I ask Carolyn a question that will lead to this?
Okay.
Carolyn, when you showed your last example of the 2 lines of the different beakers going up, red and blue, you started with the beakers and you ended up with the graph. What if you had showed students the graph without the beakers?
I've done that before.
Right, because I know you've talked about that before. Yes. And I just found that so much more, frankly, powerful as a challenge to kids, that they had to replicate the experiment rather than run the designed experiment to get a predetermined graph.
So what Alan's talking about, especially with the motion sensor, you tell a story and then you have someone draw what they think the graph will look like. And then they have to follow and reproduce that graph. And it is extremely powerful. It just was one of those things that you wouldn't have been able to see me once I realized I couldn't show what I was doing in the room as much with this. So maybe another time. Okay.
Right. So I just think the order of things is important. That's all. And then Eric, I don't know, do I have another minute or I can finish it? Pardon?
Go ahead. You have another minute.
Okay. Maybe I could share my screen again and just show one quick thing. I'm fascinated by fake news. And let me show an example of, I'm fascinated when students are home, whether it's school or COVID, that they're using Google, looking at the top screen of results, and that's what they think is true. So if you were to type in mouse, ear, BBC, this is what you'd come up with, is ear on the back of a mouse. By the way, this is not Photoshop. This is actually a real mouse. Actually lives in Boston. They use it for research. What's fascinating is when you show another source on the same content. I don't know if people can see this, but here's the same mouse in Wikipedia. The Wikipedia article says that this mouse was implanted. The ear was shaped first and then implanted. The BBC article says that the ear grew out of the back of the mouse. So those are two different action verbs, but this, in the age of the web, I am convinced that what we need to do is show students different versions of the truth so that they can develop strategies for finding primary source and so forth, that they reconcile where does the truth really lie. And I'm worried that research at Stanford and other places has shown that students don't have these skill sets by and large in the United States. So if we were to go to Google, the general rule, by the way, is no adverbs, no adjectives, no verbs. Ear, mouse, site, edu, and we know vacanti. So what I'm doing is I'm giving a quick little demo on the grammar of doing a search. You'll notice no adverbs, no verbs, no adjectives. The site : is a command that limits my results to websites with an edu extension. Vacanti is the author. You have to have that to do a primary source. There's your primary sources. MIT, it was implanted. So what I worry is that we're not giving kids a structured approach to doing really good research about understanding how do you test whether something is true or false. And I'm just praying that more teachers will do things like this, where they show different versions of the truth and then show students strategies for finding the original scientific research rather than rely on what the Google results are in the top screen. So I'm going to end there, Eric. Thanks so much for the opportunity. Thanks, Carolyn and Bob. I am always fascinated by your work. It was an honor.
Thanks so much to all three of you. This was absolutely wonderful. I hope we can continue to communicate. And one of the things that is very likely to emerge from this whole workshop is that we will start a network that support each other, and everything that the three of you have contributed is so relevant to it. So thank you again. Thank you for your time and for your input. We all appreciate this tremendously. You can click the applause button in the participant list or give a reaction like I'm doing right now. So thank you so much. We'll have a 2-minute break, and then we'll start with the next speaker, Carolyn Crouch, who is going to continue to talk along this theme of delivering the content of physics in the context of a story, although the story really is another discipline, namely the physics of, the life sciences. So we'll make that transition in 2 minutes, 11:45.
Eric,
yes.
I need to say something before we go on. So
absolutely.
Because we're going to talk about creation of this network, I think it's extremely important the last session this afternoon for everyone to participate.
Absolutely.
Well, thank you, everyone. Appreciate the opportunity to talk with you all and to listen to you, Carolyn.
Really enjoyed it.
Thank you. Thank you, Alan. Thank you, Carolyn.
Alan,
Thank you, Bob.
Alan, where was the calculus resource that you showed?
2007.
No, but where is it?
I'll send you the link, but it's if you Google pre-cal 40S as in Sam, the pre-cal is one word, 40 S as in Sam.
Okay.
You'll come right to it.
Wonderful. Thank you so much. It was great.
Thank you.